Assalamu alaikum. So we were doing complex numbers, and we were actually doing the last concept that we had in this topic, and that was loci. We started this in the last session. Let me quickly remind you what we did in the last session, and then we'll do some practice questions in this, and that will just wrap this topic up for us as well, and we'll be done with all the P3 topics that we had to do. We might spend one more session in complex numbers to do some more practice. That might be tomorrow or the day after tomorrow. But in terms of concepts, we should be done after this class. In fact, we're done with the concepts already, but there are some variations that come in loci that I want to cover in today's class in particular. So what exactly did we do in the last class? We talked about fixed distance from a point. So we talked about some loci, first of all, that we need to remember from O-levels. There are two specific types of locus that you need to remember. One is when you're looking for points that are at a fixed distance from another point. All right, so let's say you have a point O here, and you want all points that are at a fixed distance, let's say 3 centimeters from the point O. What's going to be the locus of all those points? It's going to be a circle like this. So if you want to be at a fixed distance from a point, the locus turns out to be a circle like this. If you want to be at an equal distance from 2 points, we looked at this in the last session, the locus that you get in this case is a perpendicular bisector of the line joining those 2 points. So let's say you have to find the locus of all points that are at an equal distance from A and B. Where could those points be? Anywhere on the perpendicular bisector of the line joining A and B. So it will be the perpendicular bisector of AB. So these are two loci that we need to remember. Now, how is that related to complex numbers? We talked about this. For example, if somebody says modulus of z is equal to 4, that means the distance of this complex number from the origin should be equal to 4, because that's what the definition of a modulus is. Modulus gives you the distance from origin. So if the modulus of z, which is the complex number, is equal to 4, what that means is the distance of z from 4 should be equal, distance of z from origin should be equal to 4. So the locus that you get in this case is a circle with center O and radius 4 units. Okay, that's the circle that you get in this case. If you had modulus of z less than or equal to 4, that would mean the point z could be anywhere inside the circle, right? So you would shade all the region that is inside the circle. Now, it does not necessarily have to be z every time. You could also have something else other than z inside. For example, z minus something. This is how you read that or understand that statement. Modulus of z minus a. What does that mean? This statement in particular means distance of z from the point A. You have to remember this notation. Modulus of z minus a. How do you understand that? It means distance of z from the point A. So whenever you have something in modulus form like this, the first thing you always have to do is convert that to this form. Okay. So now, keeping that in mind, what if you have something like this written, modulus of z minus 2 equal to 3? This statement means distance of z from the point 2. That's what you have on the left side. That should be equal to 3. Now, how do you draw this locus? You first of all draw this point 2, right? You compare it to the standard form. The standard form is z minus a. What do you have in place of a here? You have 2. So you're going to mark that point 2 first of all on the Argand diagram. That comes here. And now you want that the distance of z from the point 2 should be equal to 3. So where could this point z be? It will be anywhere on the circumference of the circle such that the center of the circle is equal to, is at the point 2, and the radius of the circle is equal to 3. So the distance of the point z, therefore, is going to be 3 units from the point 2 at all times. This is what we did. We did some more examples in this. If you had z minus 2 minus 3 iota, that would mean distance of z from the point 2 minus 3 iota should be equal to 1. We looked at the locus for that. If you do not have something in the standard form, for example, if you have z plus 3 minus iota, and you have modulus of that, and that equals 2, the first thing you have to do is you have to convert it to the standard form. And this is what the standard form looks like, z minus a modulus. If it's not in that form, you first have to convert it to that form. So how do you do that? You take minus common from 3 minus iota. When you do that, you have minus outside here. What are you left with inside? Minus 3 plus iota. So that means the point, which is your reference point in this case, is minus 3 plus iota. So that's what you mark here. First of all, minus 3 plus iota. This is where that point comes. And now you want to be at a distance of 2 units from this point. So you have a circle of radius 2 and center at this point. All right, so this statement now means distance of z from the point minus 3 plus iota is equal to 2. This is what the locus looks like. Okay, and we also did the other type of locus. In these examples, we had modulus on one side and a constant on the other side. The locus that we used to get for such shapes was a circle. But what if you have a form like this in which you have modulus on both sides? How do you interpret this? So this is one example that we did. Z minus 2 plus iota, modulus of that equals z plus 3 plus 2 iota. You can't understand this unless you convert it to the standard form first. Okay, so that's what you do. You take minus common here, you might take minus common here so that it converts to the standard form. And then you say the left side means distance of z from 2 minus iota. Distance of z from 2 minus iota. That equals distance of z from minus 3 minus 2 iota. So now you have 2 points, 2 minus iota and minus 3 minus 2 iota. And what you're saying is there's a complex number z, there's a point somewhere on the Argand diagram that is at an equal distance from these 2 points. So we're looking for the locus of a point that is at an equal distance from 2 points. Remember what that used to be? It would be a perpendicular bisector. So you mark those 2 points, minus 3 plus 2, minus 3 minus 2 iota. Yeah, that was the other point here, minus 3 minus 2 iota and 2 minus iota. That's this point here. You mark those 2 points, and then point z could be anywhere on the perpendicular bisector of these two, of the line joining these 2 points, and that's this line. So you draw that line, and that is the locus that you get in this case. All right. So this is what we did. And then we talked about what if you have an inequality here like this. What this means is distance of the point z is greater from 2 minus iota as compared to minus 3 minus 2 iota. All right. So distance of z should be greater from 2 minus iota and less from minus 3 minus 2 iota. So the point is closer to minus 3 minus 2 iota. In this case as well, since we're talking about 2 points, you will draw a perpendicular bisector first of all, but then you will see, since the point z has to be far away from 2 minus iota and closer to minus 3 minus 2 iota, you shade the region to the left side of this perpendicular bisector, and that would give you the region that you're looking for. Okay. Then we talked about argument. So sometimes you have this form as well, argument of z that is equal to pi over 6. Let's say what that is, your point z could be anywhere on this line, the line that makes an angle of pi over 6 with the positive x-axis. All right, so point z could be anywhere on this line. But what if you had something other than z inside the argument here? For this as well, remember, you always have to convert to this form first of all, argument of z minus a. All right, so if you have argument of z minus 2, for instance, what that means is, rather than considering origin as the point of reference, because that's what it was in the previous case. In the previous case, you could write this as argument of z minus 0. In that case, your point of reference was the origin. But if you have something other than 0 here, for example, in this case, you have argument of z minus 2. Now 2 is your reference point. 2 is your reference point. So first of all, you're going to mark that point 2 here. And then you will be measuring angle from that point. The angle from the point 2, from the horizontal line at the point 2, that should be equal to pi over 4. So the line that you draw here for the locus is going to be like this. All right. So this is the locus of all points which are at an argument of 2, or argument of pi over 4 from the point 2. Okay, so in general, this is how it looks like. Argument of z minus a. How do you interpret this? Angle of z from the horizontal line drawn to the right of the point A. That is what the statement means. So if you have, for instance, argument of z minus 3 iota, again, the reference point in this case is 3 iota. If you compare the two, in place of a, you have 3 iota. So this is equal to pi over 3. You take this as the reference point, and you draw this locus of pi over 3 from that angle, aligned at an angle of pi over 3 from this point 3. You're not going to draw this from the origin. You're going to draw this from the point 3 instead. Okay, and we did some other examples in this as well. Sometimes the form is not the standard form already. You have to take minus common. And if the argument is negative, you have to go in the clockwise direction like we did here. So the reference point was minus 1 plus 2 iota. That was right here. And then the angle from this point had to be minus 2 pi over 3. So we went in the clockwise direction. And that gave us this particular line. That turned out to be the locus that we were looking for. The point z could be anywhere on this line. Right, minus 2 pi over 3 is 2 pi over 3 is 120 degrees. So we are looking for 120 degrees in the clockwise direction here because the angle is negative. That's why we go in the clockwise direction like this. Okay, and then we also looked at what happens if you have to find the region which is described using an inequality like this. So it says argument of z from minus 1 plus iota. So this is the reference point that you have, minus 1 plus iota. The argument from this point should be between 2 pi over 3 and minus pi over 2. You draw those two lines and then shade the region between those two lines. And that gives you the locus that you're looking for. So these were all different cases that we did in the last session. Now let's look at some practice questions on this and see what kinds of complications can come here when you are finding, when you have to sketch locus of equations or inequalities like these. And then we'll also do some general rules that you need to remember when you're working with loci. But before that, let me just open this worksheet quickly and do a couple of questions from that. So we develop some understanding of this first of all. Okay, I'm going to start with this one. This is question number 41 from the worksheet. Now I'm going to be focusing on the Argand diagram and loci questions for now. So if there are any other parts involved there, I'm going to skip them. We have done enough practice on them already. So this is question number 41 from the worksheet. Let's have a look at this. Now, the first part is that you have the complex number u given, which is 7 plus 4 iota divided by 3 minus 2 iota. This is the complex number that you're given. You have to express u in this form, x plus y iota, where x and y are real. You can do this. We've done this multiple times. All you have to do is multiply and divide by the conjugate of the denominator. So we'll multiply this by 3 plus 2 iota and also divide by 3 plus 2 iota. Simplify this and you'll get the result. Let me see what this should turn out to be at the end. I'll just use that. So when you do this, you should be getting, u equals 1 plus 2 iota at the end. All right, so this is an exercise for you. We can do this. I'm going to move on and look at this next part after this. The next part says, sketch an Argand diagram showing the point representing the complex number u. This is the complex number u now, 1 plus 2 iota. Show on the same diagram the locus of the complex number z such that Z minus U modulus is equal to 2. Now let's try this. So we have to draw an Argand diagram. Let's draw that. Let's say this is how it looks like. We have the imaginary part here, the real part here. Now, whenever you draw an Argand diagram and you have to draw and you have to draw a loci on that, make sure the scale that you use in both axes is equal. So, for example, the distance that you are representing 1 by on the vertical axis, it should be the same on the horizontal axis. Otherwise, your locus is not going to be correct. Your circles will not look like circles. Your perpendicular bisector will not look like a perpendicular bisector, and that will make you lose marks. So the scale in both axes should be the same. Now, first of all, they say you have to mark this point 1 plus 2 iota. Where is this point going to be? 1 on the horizontal axis, 2 on the vertical axis. So that's this point here. This is the point U. So that's one thing that we had to do. We have marked this point U here. Now we have to draw the locus of the complex number Z such that Z minus U modulus is equal to 2. Now, first of all, let's try to understand the statement. So it says modulus of Z minus U is equal to 2. Now remember how we interpret this thing. This means distance. Remember, when you have modulus here, that represents distance. Distance of Z from U. So it's the distance between Z and U. That is equal to 2. So it's a point Z equal to be anywhere at a distance of 2 units from the point U. So U is the reference point. It's the point of reference. From U, you can be 2 units away. What's the locus of that? It's fixed distance from a point. The locus that you get in this case is going to be a circle of radius 2 and center at the point U. Now, when you do this, please make sure that you use a compass for this. Otherwise, the next parts after the locus part, they are going to become very difficult for you if the diagram is not good enough. Okay, so make sure that you're using a compass for this and your diagram is reasonably accurate. It will help you in the next part after that. So your circle has to be of radius 2 units. Let's say this is how the circle looks like. Just take this here now. 2 units should be the radius. So when you are drawing this, keep this in mind. On your diagram, your circle should pass through these points. So this point where you have 1 and 4, and then this point, because these are all 2 units away, right? So this is 2 units away. This is 0.32. This point is minus 1 and 2. And then this point, 0 and 1 and 0. These are important points. Your circle has to pass through these 4 points. That's very important. Otherwise, your calculations after this might turn out to be wrong. Okay. So this is the locus that we get in this case. It's a circle with radius 2 centimeters or 2 units and center at U. That's what we had to do in this part. Okay. Let's look at the next part now. The next part, it says, find the greatest value of argument of Z for points on this locus. And that's a 3-mark question. Now for this, you have to use your diagram. So it's really important that you've drawn the previous diagram reasonably accurately. Otherwise, you'll find it very difficult to understand what's going on here. So what you're looking for now is the greatest value for the argument of Z. That is what you want to figure out. Greatest value for the argument of Z. So Z is a complex number that lies anywhere on the circumference of the circle. It lies anywhere on the circumference. What's the greatest possible value for the argument of Z? That is what we need to figure out. Now let's try to understand this. How do you calculate, how do you measure argument? Argument is measured from the positive x-axis, right? We have done this before. Argument is measured from the positive x-axis. Now, z could be anywhere on the circumference. Let's say z was a point here. What would be the argument for that? The argument would be this angle. What if z was here? The argument would be this angle. So you can keep going on to the left and your argument will keep on increasing. All right. So if it was here, your argument would be even bigger. We are looking for the greatest possible argument. Now, how can we find that? Let's think about it. Let's see how we can find that greatest possible argument. So the angle has to be measured from the origin, right? So if z was here, argument would be lower. We can keep going forward. The argument will keep increasing like this. It will keep increasing and keep increasing until we reach a point such that the point z is somewhere on the circle such that the line coming from the origin makes a tangent with that point. If point z was here, that would give us the greatest possible angle. If it was any less than this, if z was here, this would be a lower angle. It would be a smaller angle. So the greatest angle is going to come when point z is such that the line that you make from the origin to that point z makes a tangent like this. And now this value of the angle represents the greatest argument. And this is what we have to figure out now. We have to figure out the value of this theta now. Okay, so now the problem is just reduced to finding this angle, which is now simple trigonometry or trigonometry. You can find the value of this angle somehow. Now, let's see how we can do that. Now, in locus, you'll find a lot of times whenever you have tangents like this, you'll have to use some circle properties and trigonometry. So in this case, you have a tangent coming from the origin that's touching the circle on this side. And you have another tangent going in the other direction like this. So it's two tangents coming from a single point. If I were to join the center of the circle with the origin like this, remember the property? This angle theta is going to be bisected. So if this whole angle was theta, this would be theta over 2 and this would be theta over 2. The angle would be bisected. And now if we can find one of these angles, we can find the other one as well. We can find the total angle as well. Let me call this angle something. Let's call this alpha. Only this part, just this part. Let's call this angle alpha. How can you find the value of this alpha? I can make a right angle triangle here. So if I draw a vertical line from here like this, this is the radius, this is the tangent. Radius and tangent make a 90 degrees with each other. So we have a right angle triangle that looks like this. And in this right angle triangle, do we know the height? Yes, we know the height is 2. Do we know the base? That's 1. We have this 2 and this 1. We can find the value of alpha pretty easily. We can say 2 is perpendicular, 1 is the base. What's the ratio between perpendicular and base? It's tan. So we could say tan of alpha, that equals opposite over adjacent, 2 over 1. And that would give us the value for alpha. Tan inverse of 2, you can see what that turns out to be. Remember, we always use radians here. Okay. So make sure your calculator is in radian mode, find the value of alpha from here. Tan inverse of 2, that is giving me 1.107. That's the value of alpha that we get from this. Now, we were not looking for just alpha, we were looking for this complete angle, right? This complete angle. How do you find that complete angle? You just multiply alpha by 2, and that will give us that complete angle, which we called theta earlier. So you can say theta is equal to 2 into 1.107, and that gives us 2.21. And this is the greatest possible value for the argument of z if it was on this circle, on the circumference of the circle. This would be the greatest possible value for the argument of z. All right, so I hope that makes sense. This is how we can find greatest value for the argument like this. Okay, so you'll find these problems coming up again and again where they ask you to find greatest value of the argument or the least value of the argument or the greatest value of the modulus or the least value or the least value of the modulus. Let's do one more example. And then I'll tell you some general rules that you can follow in problems like these after this example. Let's try another one. This is question number 16 from the worksheet. Now, for this, I am going to look at a particular part as well. Okay, yeah, let's do this. This is question number 16 from the worksheet. This looks like an interesting one as well. Okay, so it's a 10-mark question in total. I'm not going to do the first part. Let me just see what the answer for that is going to be. The complex number u is defined by this. U is equal to 6 minus 3 iota divided by 1 plus 2 iota. You have to show all your working and find the modulus of u and also show that the argument of u is minus pi over 2. So first part you can try yourself. Again, you'll multiply and divide by the conjugate. It will become 1 minus 2 iota over 1 minus 2 iota. Simplify this, you get u in the form x plus y iota first of all. And when you're done with that, you can find the modulus and the arguments from that. Now, let me just see what this is going to turn out to be. This is question number 16. Let's see if I can find that here. Okay, let's just open that here. Question number 16, first part. Okay, the first part should give us minus 3 iota. Okay, so you will simplify to minus 3 iota. And when it simplifies to minus 3 iota, you can figure out that the modulus of u is going to be just 3 because this is a point that lies on the vertical axis. On the imaginary axis, right? The distance from origin is going to be 3. And the argument you can figure out that is going to be minus pi over 2 because again, it lies on the vertical axis on the lower side, on the negative side of the vertical axis. So the argument of u is going to be minus pi over 2 here. Okay, so let's assume you've done the first part. Let's focus on the second part for now, on the second and third parts. In the second part, it says, for complex numbers z satisfying, argument of z minus u equal to pi over 4, find the least possible value of modulus of z. Now, how do we think about this? First of all, let me just write that here. It says argument of z minus u, that is equal to pi over 4. So first of all, before we can find this least possible value of modulus of z, we need to represent this locus. Okay, where exactly can the point z be? How do you understand this? It means the angle of z from the horizontal line at u, that is equal to pi over 4. That's how you understand the state. Now, you don't have to write this down. This is just for your own understanding. But how do you interpret the statement? That there is a point u somewhere on the diagram, There's a point U on the diagram. You are measuring angle from that point U. That angle should be pi over 4. Okay, that's what it means. Now let's represent this here. We have this Argand diagram. We have the imaginary axis here, the real axis here. Origin at the center. The scale on both axes should be the same. Be careful about that. So I have 1, 2, 3 here, -1, -2, -3 here. You have 1 here, 2 here, 3, 4. You have -1, -2, and so on. Now, first of all, you have to mark that point U. We found that U in the first part. U is equal to -3 iota. Let's write that down here on the side. U equals -3 iota. We know that from the first part. Okay, let's mark that point here. -3 iota, that's going to be this point here. And now what you want is the argument of Z, the angle of Z from the horizontal line drawn at the point U. So what you're going to do is you're going to draw a line that's to the right of U like this. You're going to measure angle from this line. That angle has to be pi over 4. Pi over 4, if you think about that in degrees, it's 45 degrees. Now, if you're drawing this line without a protector, please keep one thing in mind. A 45-degree line has a gradient of 1, which means the distance that it covers horizontally, let's say it covers 2 units horizontally, is going to be the same as the distance it covers vertically. The horizontal change in that line is going to be the same as the vertical change. Whenever you're drawing lines of angles 45 degrees, pi over 4 is 45 degrees. Okay, so when you draw this line here, from this point 3, it has to pass through the point 3 on the horizontal axis as well, because if it's covering 3 units vertically, it has to cover 3 units horizontally as well. So it has to pass through this point. That is really important. So point Z, therefore, could be anywhere on this line, such that this angle that you have here, this angle is pi over 4. Point Z could be anywhere on this line. Okay, so this is what point, this is where point Z could be. Now, what they've asked us to find is the least possible value of the modulus of Z. That's what we have to figure out. Let me write that here. We're looking for the least possible value of modulus of Z. Remember what modulus of Z represents? It represents distance from origin. Now we have a line here and we have the origin. The origin is this point here. So we have to look for the shortest distance from the origin to this line. Remember, what's the shortest distance between a point and a line? It's the perpendicular distance. So the shortest distance from origin to the line where the point Z could be is this perpendicular line. We need to find the length of this line, which is perpendicular here like this. If you're able to figure this out, that would give us the least value for the modulus of Z. All right. Now, how do you figure this out? Again, you have to use some trigonometry here. What can we do? Do we have any lengths here? You see, you know that the angles are pi over 4. So if this angle is pi over 4, what about this angle? This angle is also going to be pi over 4, right? Because the total is pi over 2. So the total angle is 90 degrees. If one is 45, the other is also 45. If this is pi over 4, then this is also pi over 4, right? So it's an isosceles triangle. It's an isosceles triangle in which if this length was x, this other length would also be x. It's a right angle triangle, which is an isosceles triangle. It's an isosceles right angle triangle. And we know the hypotenuse of this triangle, which is 3 units. So this length here, this is 3 units. Okay. So if I were to represent this triangle on the side here, this is roughly what this triangle looks like. This is the 90 degrees angle. We have this length x, this is 3. We can find the value of x from this. We can use Pythagoras for this. Base square plus perpendicular square, that equals hypotenuse square. And that gives us 2x square equals 9x square equals 4.5. And x equals square root of 4.5. We can evaluate this and see what this turns out to be. This gives me 2.12. All right, that's the value of x that we get from this. So therefore, the least value of the modulus of z in this case is equal to 2.12. This is the minimum distance of the point z from the origin. You can't have a distance that's less than this. All right, so that is what we were looking for in the second part here. Okay, I hope that makes sense. Now, let me look at the next part. The next part says, for complex numbers z satisfying z minus 1 plus iota into u modulus equal to 1, find the greatest possible value of z. Now, what exactly does this mean? Z minus 1 plus iota times u. So first of all, what you need to do is you need to figure out where this point is. 1 plus iota into u. You have to figure this point out. Okay, let me write that down here. Part 3. So you're given that modulus of z minus 1 plus iota into u, this is equal to 1 unit. And what we're looking for is the greatest possible value of modulus of z now. This is what we're looking for, greatest possible value of modulus of z. How do we figure this out now? First of all, let's simplify this and write this in the standard form. Remember what the standard form is. The standard form is z minus a. This is the form that we want. For that, we would first need to simplify this. So z minus 1 plus iota into u. U is minus 3 iota. We know that from the first part. Now, this can be written as 1 into minus 3 iota, that's minus 3 iota. Iota into minus 3 iota, that's minus 3 iota square. That equals 1. Modulus of that equals 1. Now simplify this, and this would give us z minus, keep this in bracket, minus 3 iota square, minus iota square is minus 1, so it becomes plus 3. We have 3 minus 3 iota inside, that equals 1. So what do you understand from this statement? This means distance of z from the point 3 minus 3 iota, this is equal to 1. That is what this statement means. Okay. Now let's draw this locus and see what it looks like. You have the imaginary axis here, you have the real axis here. What you have to do is you have to first mark this point 3 minus 3 iota. So you have 1, 2, 3 here. You have minus 1, minus 2, minus 3 here. You have 1, 2, 3. 3 minus 3 iota. This is in the standard form, right? Z minus a. So in place of a, we have 3 minus 3 iota. Let's mark that point first of all. 3 minus 3 iota, that point is going to be right here. Okay. Now, distance of z from this point should be equal to 1. Should be equal to 1. So it's fixed distance from a point. There's a single point here, And the distance from that point has to be equal to 1. What's the locus in this case? The locus is a circle with radius 1. So the locus that you get in this case is going to look like this, a circle with center at this point that we have. That's the point of reference. We have a circle with radius 1 and center at that point. Okay. This is 1 unit. This is 1 unit. Now what you're looking for is the greatest possible value for the modulus of z. So again, modulus of z means distance from origin. Distance from origin. Point z could be anywhere on the circumference of the circle. We are looking for that position where the distance from origin is maximum. Distance from origin is maximum. Now, if point z was here, let's say, the distance would be like this. Now, could we have greater distance than this? Yeah, we could have z on this side or maybe here. What value is going to give us the maximum distance? Let's figure that out. You see, if point z was here, okay, sorry about that. Yeah. If point z was here, it will be a very short distance, but you can keep increasing it now. It keeps increasing and increasing until it goes to the other side like this. And then the maximum possible value of modulus of z is going to come when the line coming from the origin passes through the center of the circle and then again touches the circle on the other side. If the point z was here on the other side like this would give us the maximum possible distance from the origin. Okay, the line coming from the origin should pass through the center of the circle and go to the other side, and that will give you the maximum possible distance. Now, how do you find the length of this line? Because that is going to give you the maximum possible value for modulus. So see, this is the distance that you're looking for now. How can you find this distance? Now, again, there are multiple ways of doing this. One possibility could be that you, what are we looking for here? Just confirm that. We are looking for the greatest possible value of modulus z. Yeah, okay. Do we need an exact value? No, we don't need exact value as well. Just have any value. All right, so greatest possible value of modulus of z. This is the distance that we're looking for that you see in yellow here. How can you find this distance? Now, if we try to find this directly, we don't have the horizontal distance here. We don't have the vertical distance here. What we can do is we can actually break it down into two parts. We can say, let's call this point something. Let's call this point C. We could find the distance OC first of all. And then the rest of the distance is just 1 unit because the radius of the circle is 1. If we can find OC somehow, we can just add 1 to that, and that will give us the total distance. Can we find OC? Finding OC is pretty straightforward because we could use this right angle triangle, this triangle, and this the base is 3, height is 3. We just have to find the hypotenuse, which is OC. All right, so that's what we can do here. We can say OC squared is equal to 3 squared plus 3 squared. And OC therefore turns out to be square root of 18, which could simplify to 9 into 2, which is 3 square root of 2. That's the length of OC. So what's the greatest possible value of the modulus of z then? Greatest modulus of z would be this value OC plus this radius, which is 1. You can leave it like this if you want, or you can write some decimals as well. And that will turn out to be 3 square root of 2 plus 1, which is giving me 5.24. This is the greatest possible value for the modulus of z in this case. All right, so that's how you deal with these loci questions. Now, before we end, let me summarize some of these general rules that you would find helpful in later questions. So there are some things that you need to know about when you're looking for least or greatest possible values for modulus and arguments. Now, we've done these already in the examples that we did, but let me just summarize that. If you have to find shortest distance between a point and a line, remember that shortest distance is always going to be the perpendicular distance. Shortest distance between a point and a line is always perpendicular distance. Please remember that. Okay. Shortest distance between any point and a line is always perpendicular distance. That's the first thing that you need to remember. So whenever you are looking for the least value of modulus in which the locus is, let's say, a line, and you are looking for its distance from a point, it would be a line like this, a perpendicular line like this. All right, let me see if my internet is still working. Can you still see this? Maybe I can just check this. Can you see this working? Yeah, okay, good. So my internet is working. All right. So that's first thing. Then sometimes they ask you for the shortest distance between a point and the circumference of a circle. So sometimes you have your locus as a circle, right? So like this. Your locus is a circle. Your point Z could be anywhere on the circumference of the circle. And you have to look for the shortest distance from a point to the circle. So let's say you are looking for the least value of modulus from a particular point. So let's say P is the point. Sometimes it's origin. It could also be something else. How would you find the least possible distance from this point P to the circumference of the circle? Now, you would have this distance here. Can you make it shorter? Yeah, you can make it shorter. You can make it shorter. You can keep making it shorter such that it becomes shortest somewhere around this point here. Now, where exactly is this point going to be? This point is going to be when you join P and the center of the circle. When you join P and the center of the circle like this, the point where this line touches the circumference, this distance is going to be the shortest distance. All right, so if you're looking for the shortest distance between a point and the circumference of a circle, what you do is you draw a line from that point to the center of the circle. And then the point where that line cuts the circumference, until that point, you would have the shortest distance. So this represents the shortest distance in this case. Okay, so this is the shortest distance. All right. Now, what if you were looking for the greatest distance between a point and the circumference of a circle? It works very similar to the previous case. Let's say you have the center of the circle somewhere here. What you would do is you would draw a line that goes through the center of the circle like this and touches the circle on the other side. This point is going to give you the greatest distance between the point and the circumference of the circle. When the line coming from that point passes through the center of the circle and touches the circle again on the other side, this would give you the greatest distance. Okay, so if you were looking for the greatest value for the modulus of a complex number Z, such that this was the origin, or maybe if you were looking for the greatest distance that point the locus could have from a particular point, and the locus is a circle, in that case, this is the idea that you use. The greatest distance is going to be when you pass through the center of the circle and touch the circle again on the other side like this. Okay, so this is an important thing to remember. And then sometimes you're looking for the least and greatest arguments. for points on circumference. So for example, let's say you have a point P here, okay? And the locus that you have is a circle. What you want to do is you want to find the least value of the argument for points on the circumference. Where is going to be the least value of argument? So let's say this is the origin, this point is the origin. You're looking for the least argument. How do you get the least argument? The point Z, the complex number, could be anywhere on the circumference. It could be here, here, here. Argument is measured from the horizontal line. So if you had a horizontal line here, you would be measuring angle from that. How would you get the least argument from this line? If you had a line coming from this point origin to the circumference here like this, can you make this angle smaller? You can keep making it smaller and smaller and smaller until you reach this lower end of the circle, such that the line makes a tangent with the circle. Now, you might think it's the lowest point on the circle like this. It's not. Let me actually make it slightly clearer. Let's say the point O was even below this. It does not necessarily have to be the lowest point. It could be something else as well. So for example, if O was here, the line coming from the origin is going to be like this, such that it makes a tangent with the circumference of the circle on this, or on this side. This point, let's call this point Z1, is going to give you the least value for the argument. Let's call this value angle θ1. This is the least argument that you get in this case. So whenever you're looking for least argument for the points on a circumference, it's going to come using a tangent like this. Similarly, what about the greatest argument? For the greatest argument, again, you could have a line coming from the origin. And how can you keep increasing the angle? You can keep going to, you can keep increasing the angle like this, such that you go on the other side here. And you get a tangent on the other side of the circle like this. So if the point Z was somewhere here, this would give you the greatest possible argument for points on the circumference of the circle. And that greatest possible argument is going to be this. Let's call this θ2. This would be the greatest possible value for the argument of the point on the circumference. All right, so if you're looking for the least argument or the greatest argument, what do you have to do for that? You have to draw tangents to the circle. On one side, you would get the least argument. On the other side, you would get the greatest possible argument. All right, so this covers pretty much all complications that you could get in Loci, but of course, you should do more practice. In the next class, we will just be doing some practice questions. I'll confirm when that class is going to be. It might be tomorrow or the day after tomorrow. Most likely the day after tomorrow. I might not be able to do it tomorrow. So we might have one more class on some past paper questions. I'll try to make it slightly longer so we can do as many as we can. And then we would wrap this topic up. In fact, and we're done with the concepts that we had to cover. But we'll do some more practice in the next session, inshallah. All right, so I hope that was helpful. I'll see you again in the next session. In the evening today, remember, I'm doing March 2023 paper 5 S1. I'm doing that in the evening session today at 4:30. And then tomorrow I'll be doing March 2023 paper 3 as well, inshallah. All right, and then M1 the day after that. Okay, I'll see you again later in the evening then. Allah Hafiz.